Mr. Strauss's class is filmed before a live studio audience. No laugh track was used in this presentation. You may not use this video without express written consent from Mr. Strauss or his subsidiaries. Okay, so we are in chapter 19, which is gas laws. And all we're going to do now is take the ideal gas equation which is PV equals nRT, or I could combine that with stoichiometry. So stoichiometry is using mole relationships to find out how much of a product you're going to get. So we start off with a reaction. In this case, I'm going to do the combustion of gasoline. Do you remember what we get, Adam, when you combust a hydrocarbon? Your two products?
Water and carbon dioxide.
Okay. These problems are called volume to mass, because what we're going to do is we're going to be given a volume of gas, and we're going to calculate the mass of a product. So let's balance the reaction out. We have 8 carbons. I'm going to need 8 carbons. That means 16 oxygens. Actually 17 oxygens. Now let's leave the oxygens. Let's go to the hydrogens next. 18 hydrogens. I need a 9 there. That gives me 18 hydrogens. So now I have 16 oxygens and 9 oxygens. 16 and 9 is 25. So that means I need 25 oxygens on this side. If you want, you can use fractions. That would balance it out. That would give me 25 oxygens on each side. If you don't like using fractions, then multiply everything through by 2. And now the reaction is balanced. So here is my problem. What mass of CO2 is produced when 15 liters of oxygen at, I don't know, 25 degrees Celsius and 250 kPa is combusted. So what mass of CO2 is produced when 15 liters of oxygen at 25 degrees Celsius and 250 kPa is combusted? Now if we go back in time, what we used to do is you used to be given a mass. And you'd convert mass to moles, moles of known, moles of unknown, and then to mass. So we took the mass, converted it to moles, moles of known to moles of unknown to mass. Same process, except instead of starting with a mass, we're starting with a volume. So we have 10 liters, not 10, sorry, 15 liters of oxygen. And we want to find the number of grams of carbon dioxide. So the first thing we do is, like we did before, get it into moles. So you got to convert volume into moles. Now, how do you convert a volume into moles? Pivner. This equation relates moles to volume. So to get it into moles, do my algebra. And then I plug in my numbers. How are you doing today, Miss Moffitt?
I'm sort of out of sorts.
Sorry to hear that. You are being recorded for your own personal...
Sorry, I will leave.
No, you can come in. You're just going to be on YouTube.
Oh, goody.
All right, so pressure is 250 kPa. Multiplied by my volume. Volume must be in liters, or decimeters cubed, which is the same thing. Okay, so it must be in then divide it by the universal gas constant, which would be 8.31. And divide it by my temperature in Kelvin. So to put it in Kelvin, I have to add 273. So kPa cancels with kPa, Kelvin cancels with Kelvin, liters cancels with liters. The units I'm left with are moles. And I get 1.51 moles. This is moles of oxygen, okay? Put down what the substance is, okay? Otherwise you're going to get confused. Make sure you write down it's the O2 we're dealing with. So questions so far? So all we've done is just use the Pivner equation like we did for homework. Found the moles. Now that we have the moles of known, we're going to convert from moles of known to moles of unknown to mass. And now this is where we combine the stoichiometry. So we start with the 1.51 moles of O2. Draw your railroad track. And if I have moles of O2 up here, Trevor, what goes down there?
Moles of O2.
Moles of O2. And what's the relationship between O2 and CO2?
25 to 16.
25 to 16. So we've got 25 moles of oxygen to 16 moles of CO2. So now we have moles of unknown, and then the last step there, Rachel, is to convert to our mass. So if I have moles of CO2 here, moles of CO2 go down here. Then we add up the mass of CO2. So carbon weighs 12. There's one of them. Oxygen weighs 16. There's two of them. So carbon dioxide weighs 44 grams. that will come out to be 42, well, let's see. Yeah, 3 sig figs, 42.5 grams of CO2. So if I combust 15 liters of oxygen under these conditions, 25 degrees Celsius and 250 kPa, I will produce 42.5 grams of CO2. So again, we're really not learning anything new in the rest of the chapter. We're just using Pivner and relating it with stoichiometry. So first thing you do, get it to moles, then from moles of known to moles of unknown to mass. And it doesn't have to go from reactant to product. You can do the exact same problem, just do it the other way. I could say I have 15 liters of CO2. Find the amount of grams of oxygen, or the grams of gasoline or octane. So you can go either way. Any questions before I raise it up?
Well, is the question from yesterday, for when you were giving us the Kenson 8.31, and you put it in kPa, then you gave it to us in
Atmospheres.
atmospheres, so when would we use that?
If the pressure is in atmospheres, then you have to use the universal gas constant that's in atmospheres.
Okay.
We'll do one more problem, and then I'll give you time to work on your homework and labs. So, there's really only one other thing we can combine here, and that's limiting reactants. And so let's say we have this equation. We've got hydrogen gas reacting with nitrogen gas to produce ammonia, which is also a gas. Balance it out, we're going to need a 3 here, a 2 there, and we're balanced. If 10 liters of hydrogen gas at 0 degrees Celsius and 50 kPa react with 15 grams of nitrogen, how many grams of ammonia are produced? So I've got hydrogen gas reacting with nitrogen gas to produce ammonia. I want to find out how many grams of ammonia are produced. So it looks like the last problem in that we've got a volume, 10 liters, of a gas. We're trying to find the number of grams produced of our product. The only difference is now we also have the amount of the other reactant, 15 grams. So if you have 2 amounts of 2 reactants, you have a limiting reactant problem. You got to figure out which one's going to run out of first. Are we going to run out of hydrogen first? Or are we going to run out of nitrogen first? So just like before, we have to do 2 problems. One problem with the hydrogen, one problem with the nitrogen. So maybe we should do the nitrogen one because it's been a little while. So take 15 grams of nitrogen. You have grams on top, grams going on the bottom. We're trying to get it to moles. So if you're given mass, get it to moles. If you're given volume, get it to moles. So nitrogen weighs 14, and there's 2 of them, so it'd be a mass of 28. And once I get it into moles, then what's my next step, Kelly?
Compare it to ammonia.
Compare it to ammonium using the mole ratio. So for every one of these, I get 2 of those. Now what we can do is we could stop here. We don't have to do that last step yet to convert it to mass. We could leave it here as moles of ammonia. Now let's just do that. It will save us a little bit of work. So I have 1.07 moles of ammonia. Now we go to the other reactant, the hydrogen, and we do the same thing we did in that previous problem. We're going to use pivnert to get it into moles. So my pressure is 50 kPa multiplied by my volume. The volume must be in liters. Divided by R, 8.31. And then divided by my temperature, 0 degrees Celsius is 273 Kelvin. And I get 0.220 moles of hydrogen. So this is where, again, it's important you write what the substance is, because right now we can't compare the two, because that's ammonia, that's hydrogen. So we got to convert moles of hydrogen into moles of unknown. What's the relationship between hydrogen and ammonia? 3 to 2. So every 3 moles of hydrogen will give me 2 moles of ammonia. And I get 0.147 moles. So now you can compare the two. Which one is the smaller number there, Sam?
Hydrogen?
The the hydrogen. It gives us 0.147 moles. So you go with the smaller one. And so you can, like I said, you can stop at this point and compare the two. Then take the smaller one and convert it to mass. So I would take 0.147 moles of ammonia, the smaller number, and then convert that to grams. And 1 mole of ammonia is 17 grams. So the answer would be 2.50 grams of ammonia produced. And that's your answer. Which one's the limiting reactant? Sarah, do you remember?
H2.
Yeah, the one we run out of, that's the limiting reactant. Okay, so we need more hydrogen. The excess is the nitrogen. And this is the theoretical maximum that we can produce. Now, if you go into the lab, do you ever get the theoretical maximum? No, you always get less than what you think you can get. So we can also do a percent error problem, a percent yield problem, because once you know the theoretical max, then you could, do like we did in the lab and calculate percent error. So, all right. Any questions? In that case, I'll give you some time to work on your homework or your labs.